All right, here we are, chapter 1, section 1. We're going to talk about functions. And before we do that, we are going to talk about relations. Relation is a set of ordered pairs. The set of first components of each ordered pair is called the domain. And the set of the second components of each ordered pair is called the range. Now, the domain is what we call an input value or an independent variable. And we usually use the lowercase x to represent that. And as far as the range goes, that's the output value or the dependent variable. And we usually use the letter y for that. And let's jump to the definition here of a function. A function is a relation in which each possible input value leads to exactly one output value. And so this can be explained very nicely with a diagram here. These are relations, these pictures here. And you can see this is our domain and this is our range. And you can see each x value is being mapped to exactly one range value. Now, it doesn't matter that two different x values are being matched to the same range value. That's okay. It's still a function. This particular function is mapping exactly one x value to each y value and or one domain value to one range value, and it also is exactly one range value maps to exactly one domain value. So that's referred to as a one-to-one function. We'll talk about that a little bit more in a moment. And relation here, this is not a function, to be clear, definitely not a function. And we know that because we have this domain value being mapped to two different, so one x value can't map to two different y values, or one domain value cannot map to two different range values and be a function. We often use this notation here, y equals f of x, and we say y is a function of x. And x again represents the domain or input value or independent variable, and y represents the f of x, which is the output or dependent variable. So which of these tables are going to represent a function? Well, once again, this one is very nicely. Each one is mapping to a different y value. So this is definitely a function. This one, even though two different domain values are mapping to the same value, this is still a function. This is still okay. However, you can see that we have one domain value mapping to two different range values. This is not a function. And here we have, we're going to do some algebra with the functional form. So here we have f of x equals x squared plus 3x minus 4. And we're going to do several different, here we'll start with part A, where we're looking for f of 2. That means I'm going to replace all of the x values in the function with a 2. Make sure you put parentheses around the number, because if it's negative, you'll have to square the entire negative number. That doesn't apply in this case, but in other cases it could. So f of 2 is 6. And to be clear, this is the range value. And this, the 2, is the domain value. Part B says we're going to find f of a, meaning some generic number. Well, that's very easy to do. And that's it. We can't go any further with that. We're done. Now C is going to take up some real estate here. So I'm going to replace all of the x values with an a plus h. So this is going to be f of a plus h. It's going to be a plus h squared plus 3 times a plus h minus 4. Now I'm going to FOIL that first one together. Distribute the 3. Minus 4. Now all of that is the answer, and even all of that I'm going to use for part D. It says find f of a plus h and subtract f of a from that. So that's basically part C minus part B, all over h. So here we go. Now I'm going to subtract part B here. So I'm going to subtract that. So I'm going to change all the signs on this. So it's going to be minus a squared minus 3a plus 4 all over h. Now, what's really cool about this is we get to start slashing stuff out. So a squared minus a squared, 3a minus 3a, negative 4 plus 4. And this here is actually called the difference quotient and is used in calculus. So this is actually very important. What's left all have h's in them. So if I factor out an h and reduce it with the denominator, I end up with 2a plus h plus 3. And believe it or not, you just did calculus the long way, which you'll do at the beginning of your calculus class when you get there eventually. For example 3, they want us to now take, instead of replacing p with something, they want us to replace h of p with 3. So I'm going to subtract that to the other side, and we're going to end up with a quadratic. And this one factors. If it didn't, you would have to use the quadratic formula, of course. This tells us that p is negative 3 and 1. All right. For example 4, they want to know when x equals 2. So here's x equals 2. So we're going to here. What does y equal? Well, it looks like y is going to equal 1. Here they're saying when y equals 4, that's up here, they want to know what x values we hit. Well, it looks like we have 2 values. We have one here and we have one here. So it looks like x is going to be negative 1 and 3. Now, how do we determine if a graph is a function or not? Well, we're going to use something called the vertical line test. And the vertical line test basically says that every vertical line that crosses the graph should only cross it no more than one time. If it crosses it more than once, it's not a function. And you can see this first one here is a function. Right here, so we got a function here. However, here we have an issue. You can see this is crossing the graph twice, once here and once here. Same with this one, we're crossing twice. So if any vertical line crosses more than once, it's not a function. We would still call it a relation though. Now, if we want to determine if a function is one-to-one, meaning every x value or domain value maps to exactly one range value and every range value maps to exactly one domain value, then we would use something called the horizontal line test. And this determines if it's one-to-one or not. If a horizontal line crosses a graph more than one time, it is not a one-to-one. So we can see in this first example, I can draw a horizontal line and it crosses it more than once. So this is not a function. Not one-to-one, pardon me. Neither is this one. However, you can see here, every horizontal line is going to cross it more than one time. So this one is 1-to-1. And we're going to end our session with some graphs here. So we have a constant function. We have f of x equals x. We have absolute value, x squared, x cubed, 1 over x squared, root x, and cube root of x. These are all of our basic graphs. These are all graphs that you really should know going into calculus, at least the basic ones, and hopefully some of the shifts as well. So let's talk about this here. Here we have f of x equals a constant. This is going to be a horizontal line that crosses at C. For this one, this is going to be exactly the diagonal line here. Now, we could rewrite this y equals mx plus b, 1x plus 0. And you can see it crosses at 0 down here. And we use the slope up 1 over 1 to get to the next point. And so there's our diagonal line. For our absolute value, we end up with, these are supposed to be straight lines, pardon me. This here, now this line here is actually the same as this line over here. But when it hits the x-axis, because of the definition of absolute value, its slope becomes negative, and all the x values we can see are going to be positive here, or the y values are going to be positive here. Y equals x squared is our parabola. With a vertex at 0, 0. X cubed is going to look like this. It's going to come down and it's going to cut right through the origin and keep on going. 1 over x has kind of a weird looking graph. It's very asymptotic. It is never going to cross the x or the y axis. And 1 over x squared looks similar to the 1 over x, except this one, the y values are always positive. And again, this will never cross the x or the y axis. F of x equals root x is going to do this. It's going to be a sideways parabola, but only the positive parts. And y equals x cubed is going to cut through like this. And that is going to be it.